Okay, so now we will talk about the chapter 13, Congruence on integers. So previously we have talked about prime factorizations, fundamental theorem of arithmetic, and then we have talked about in chapter 12, we have talked about more on prime numbers, where we have talked about there are infinitely many primes given by Euclid, and then some conjectures about it. And then we have solved some exercises. So in this chapter, we talked about introduce another method for studying the integers called congruence. So let's define it. Definition. So let m be a positive integer, then for a comma b is integers if m divides b minus a, we write a is congruent to b mod m, and say a is congruent to b modulo m. Okay, this is a definition for the congruence. Now, for example, we have 5 congruent 1 mod 2. This means when we divide 5 by 2, we will get the remainder 1. Similar, (12) mod 17 congruent 17 to mod 5. If m divides b minus a, this is also true. So 17 minus 12 divides 5. Yeah. Similarly, we have also one is 91 minus congruent to minus 17 mod 12. So 91 plus 17 is 108, and it is divisible by 12. Similarly, the other one is 531 is not congruent to 0 mod 4. So 531 is not divisible by 4. So these could be the examples. Now proposition. (13.1) it says that every integer n is congruent to exactly one of the numbers 0, 1, 2, dash up to m minus 1 modulo m. We can prove this. So proof, we say that let x belongs to the integers by proposition 10.1. There are integers q comma r such that x is qm plus r with r between 0 and m. Thus, then x minus r is qm. So m divides x minus r, and hence by the above definition, x is congruent to r mod m, since r is one of the numbers 0, 1, 2, up to m minus 1. Hence, we have proved it. So every integer n is congruent to exactly one of the numbers modulo m. Okay. Now we have some examples. Thirteen point one. So number 1, every integer is congruent to 0 or 1 modulo 2. Every integer is congruent to 0 or 1 modulo 2. Indeed, all even integers are congruent to 0 modulo 2, and all odd integers are congruent to 1 modulo 2. So indeed, all even integers are congruent to 0 modulo 2, and all odd integers to 1 modulo 2. Perfect. Number 2, every integer is congruent to every integer is congruent to 0, 1, 2, 3 modulo 4. So if you more specifically, we can say that every even integer is congruent to 0 or 2 modulo 4, and every odd integer to 1 or 3 modulo 4. Perfect. Number 3, my clock is now showing the time is 2 a.m. What time will it be showing? Showing in 4,803 hours. Now, since 4,803 is congruent to 3 mod 24, it will be showing a time 3 hours later than the current time. So that is namely 5 a.m. Okay. Now the next result will be quite useful for our last work involving manipulation of congruence. So proposition 13.2 says that let m be a positive integer. The following are true. Following are true for all A, B, C, and Z. So number 1 is A is congruent to A mod M. 2 is if A is congruent to B mod M, then B is congruent to A mod M. Okay. Number 3 is if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. Perfect. Can prove this proposition. And there we say, number 1, now since M divides 0, we have m divides a minus a, and hence a is congruent to a mod m. 2, if a is congruent to b mod m, then m divides b minus a. So m divides a minus b, and hence b is congruent to a mod m. Number 3, if a is congruent to b mod m and b is congruent to c mod m, then m divides b minus a and m divides c minus b. Say b minus a is congruent to, b minus a is km, comma, c minus b is lm, then c minus a is equal to k plus l into m. So m divides c minus a, and hence a is congruent to c mod m. And that's how we prove the proposition. Okay, perfect. Then later on in the next part of this chapter, we will talk about more arithmetic congruences. Thank you so much. Bye.